Welcome, ladies and gentlemen. A quick video to go through the answers to chapter 7 on the AS physics book. Question number 1 says the car goes from rest to 100 kilometers per hour in 5.8. Calculate the acceleration in meters per second squared. It's 3 marks, which is nice and easy. So first up, we want to turn 100 kilometers an hour into meters per second. So if it's 100 kilometers per hour, then that's the same as 100 times by 1,000 meters per hour. Okay. Now, if we want to turn 100,000 meters per hour into 100,000 meters per second, well, meters per second, we want to divide it by the number of seconds that's in it. So basically, we're timesing it by 1,000 to get into meters per hour, and dividing it with 3,600 to get into meters per second. Now, bang that into your calculator. That gives you 27.7 recurring, so 27.8, which if we wanted to be proper about it, we would really want to give it 2 sig figs, or really 1 given the numbers in the book, but hey, let's just leave it at this for now. So that's 27.8 meters per second, ms to the minus 1. Okay, that's A. B says, oh no, it doesn't. A says calculate the magnitude of the acceleration psi. So we got that far. That's the first part of A part 1, is that, I suppose. So what we need to do to finish this off, we want to know the acceleration. Well, of course, that is delta V over T. So it's gone from rest to that. So it's basically 27.8 divided by the time it takes, which is 5.8. 5.8. So divided by 5.8 gives us 4.789, blah blah blah, like 9. So let's call that 4.8 ms to the minus 2. Okay, that is the first part, 1A, basically calculate the magnitude of the acceleration of the car in meters per second squared. Right then, B, the second part of this question. Calculate the distance travelled the car while it's accelerating. Well, we want to use one of our SUVATs. We want the speed, the distance, S, that's what we're looking for. We have the acceleration that's given to us. Brilliant. We know that, well, we've worked out the acceleration. We know the time, ka-ching. We know the initial velocity, yes, and we know the final velocity. Brilliant. So we want to basically pick any SUVAT that's got an S in it. Given that this is the thing we calculated from other numbers, there will be some rounding errors in it. So we'd be better off using this and this. And of course, the one we want using to give us S is S equals a half U plus V times by T. And that's pretty straightforward, bang, because it's also the subject of the equation. So we will put that in, a half times by 0 plus 27.8 times by the time, which was 5.8 seconds, and that will give us that will give us 80.62 or 81 meters. Happy days. That's question number 1. Alright, can we fit number 2 on this piece of paper? Yes, we can. Yeah, I'm sure we can. So, describe the motion of the train following regions of graph. So A to B, I'm going to write this down. From A to B, well, it's going up in a straight line, so it's going to be uniform acceleration. That's the first bit. That's A to B. Next bit is B to C. Well, there we go. It's constant velocity. Constant vel. That's going to be BC. And that's of course because it is a flat line, i.e. no gradient, therefore no acceleration. It's in the positive direction, but we'll come to that in a minute. Okay, C to D. Well, it's uniform acceleration, but it's negative, it's slowing down, so I'm going to call it uniform decel. Okay, that's C to D. Now be careful, you could use uniform deceleration or you could use uniform negative acceleration, but don't put a minus deceleration. It's like using a negative, a double negative, it becomes a positive. Yeah, so you could calculate what that was and say it's a deceleration of however many meters per second squared, or you could say it's an acceleration of minus however many meters per second squared. Anyway, D to E, that is a flat line on the 0 velocity meters per second on the axis basically, so it's not moving, it's stationary. Okay, stationary, I can't spell. D, E, that's that part there. Alright, E to F, well, we've got uniform acceleration again. Uniform accel, but of course we need to say something that's in the opposite direction, okay, because basically this is going in a positive direction, this is going in a negative direction. You can say in opposite direction. I suppose I could put, if I had more space, 2AB, but I'm not going to put that on there. So that would be EF. F to G, of course, is constant vel. Of course, we could say that it's constant velocity in the opposite direction. We could say whatever. Anyway, it only asks us from up to E to F, doesn't ask for anything else. So yeah, that's F to G. And this bit would be constant deceleration back to 0. Alright, anyway, that's it. It only wants it up to E to F. So, what feature of the graph represents the displacement of the train? Well, the displacement of the train is the total distance from where it started in a given direction. So it would be the area under one part of the graph, this part of the graph, minus the area under this second part of the graph. Okay, so we're gonna to put that into words. Okay, that's A. So to put that into words, we'd say it would be equal to the area enclosed by the graph. Okay, the area enclosed by the graph. I suppose leave it at that really. Between how am I going to say this? Area enclosed by the graph. Between velocity axis and time axis. Yeah, I'm going to leave it at that for now. Okay, what else? Explain with reference to the graph why the distance travelled by the train is different from the displacement. Okay, so for C, for this one here, basically the distance travelled by the train would be that whatever's enclosed under this first part, A, B, C, D, this area here, plus the distance travelled of this, okay, E, F, G, B, E, F, G, H. But, of course, this is going one direction, then it stops, and then this is coming back. So really, looking at these two, it looks pretty much like they're the same area, okay? They are the same area, I think. So this basically means the train goes off somewhere, stops a bit, and then comes back. So altogether, this ends up back where it starts. Of course, the distance travelled will be the area under this plus the area under this. The displacement would be 0. Okay, so what we want to say is to explain that into words with reference to the graph. The distance is scalar and is equal to the area under both sections. Okay, whereas the displacement is vector and is equal to the area under, let's say, ABCD minus the area under EFGH. And we could say that it's also equal to 0. I'm going to run out of space now. It's also equal to 0 because they're both the same area. Alright, that is question 1 and 2 on page 136, chapter 7.